Welcome to this new section. We should start by looking at the error sanction and loss function we shall use in training our model. This function or this loss function happens to be the Euclidean loss, which is derived from the Euclidean distance, and it goes as such. For every pixel we have in our density map, we compare it with the true density map. That's the target density map. So by doing that, we have y through I. This is for each I, where I goes from 1 to m, where m represents all the different pixels we could have in the density map. Now note that this m doesn't represent the batch size, it represents the total number of pixels in our density map. So for each of those pixels, we have y target minus y predicted squared, and then we simply add this or sum this up. Then at the end, the answer we get, we'll find its square root. Now coming back to the code, all we need to do is to define this custom loss as such. Once this custom loss is defined, we go ahead to set the learning rate, we compile the model, and we define the checkpoints. Now instead of this, we should have CSR net. So there we go. We could start with this, run that, and now we're ready to train our model. So we have this, we have our train generator, which we defined already. We shuffle number of epochs on the callback. So there we go. Note that we shall train on just 10 images from our data set. Then you could simply increase this to say 380 or 350, then with a validation of say 50. Now let's check on the error we have. We told here that we haven't this sigma. Let's go up and check. Right here we didn't do that, so we should have, this was the Gaussian radius, so we should have the Gaussian radius. Run it again, that's fine. Our model is now training quite normally. Now note that the reason why we decide to work with relatively low learning rate is because we are using fine-tuning in this VGG model right here. So we're trying not to avoid distorting the already trained weights of the VGG model. And also note that the reason why we don't selectively keep aside the batch normalization layers is because in the VGG model there are no batch normalization layers. So with that, we look at our training, everything looks fine. Also note that the most common metric in this people counting models isn't accuracy. We could actually use the mean average error or the mean square error. So we'll just work with the mean average error for now. So that's it. Now while we're training our model, we could go ahead to put out a code for prediction. So right here we have this input image just like what we had done previously. Let's take this off. We have the image, we load the image, we normalize it by first dividing by 255, and then we subtract the mean. So it's just like having x minus the mean divided by the standard deviation. So that's it. So that's kind of like what we're doing. So we have x equals x minus the mean minus divided by the standard deviation. So and we do this for each of the channels. That's why you have this right here, 0, 1, and 2, because our image has 3 channels. So for each channel, we take each value minus the mean of that channel divided by the standard deviation of that channel. So that's it. We take out the numpy as array since this is going to generate a tensor. So we get back to our training. Let's pause this for now. So we stop this kernel for now, and then we try to predict using this image from our data set. So there we go. We see that this looks quite similar to the actual density map which we had seen previously, which was, now this was this was 245. So let's pick image 1. So there is it. So it looks quite similar to this density map, what we just generated right here, the predicted density map. But then once this counting is done, that is once we have the sum of the outputs, we obtain 186 instead of 233. So it means we need to continue training, and then to come up with a model which doesn't overfit on this few images, we need to increase now our data set to take in many more images. We also continue training again up to this loss of 0.77, and then running this, we obtain this result. So we see that it's getting better. Now to get perfect results, obviously you just need to continue training, but this will overfit on the few images we've trained. So we still have to include many more images and then use data augmentation techniques to increase our data.